We're just going to have a quick look at some of the electrochemical systems that we might be using in fever, and really start from first principles on their operation. We'll go over a bit of the background, concentrate on lead acid, lithium ion flow cells and fuel cells in terms of the technologies, but most of the underlying principles sort of work for most of the systems. Just in terms of fuel cells and batteries, effectively you're looking at converting chemical energy into electrical energy through the oxidation reduction of species. Batteries tend to be a closed system, so they have a finite capacity, and primary battery is single use. Secondary batteries are rechargeable, so the reactions are reversible, and you can recharge them and use them again. With fuel cells, they're more of an open system, so you can supply the reactants to the reactor in a continuous stream and run them without recharging. So effectively they are a primary energy system because they require a constant supply of fuel. Just in terms of when we're talking about different components within packs, you've got an individual cell as a building block. You put those into strings of series connected cells to increase the voltage, and then modules. You can parallel up the strings, and then at packs you're into again multiples of modules. Just in terms of voltage and current, when you're putting together the strings and modules into larger packs, it depends on whether you are running in parallel or series. So in terms of the overall pack and system outputs for voltage, resistance and current. So in a parallel configuration, the current is split. So you've got an individual cell operating at 2.5 amps. You multiply up across the that set of cells in parallel to give the multiple of the current. The resistance is just the sum of the reciprocals of the individual cells, and the voltage stays at the cell level. When you're in series, the current stays the same, so you have the same current going through each of those cells. The resistance is a multiple of each of those in series, and as is the voltage. So you increase voltage within a pack by adding more cells in series, and you can increase the current and power output from putting multiple strings, series strings, into parallel batches. When we're talking about both fuel cells and batteries, we've got the current collectors, which are effectively where you make electrical contact and how you're going to get the electrons in and out of the cell to the external circuit. The active material is the species that are undergoing the redox changes within the system. Electrolytes form an ionic pathway within the system, so you've got electronic flow in the external circuit powering, in the fever's case, the charging of electric vehicles, whereas internal to the battery or fuel cell, the charge balance is made by ionic movement through the electrolyte, and then you've got the container and enclosure that packages everything together. If we start off with some conventional batteries, and effectively it's going from the original Volta pile through to something that we can charge electric vehicles, whether they're bikes or cars, in the fever case study. And just for nomenclature, industry uses anode and cathode, which is fine for primary systems, but when you start to recharge, it can become a little bit confusing. So the negative electrode is always at a potential that is more negative than the positive electrode. So in a discharge state, the negative electrode acts as an anode with oxidation occurring, and the positive electrode acts as a cathode with reduction. When you reverse that process to recharge the system using a power supply, the anode and cathode actually change. So the negative electrode stays negative, positive electrode stays positive, but you have reduction and a cathodic reaction at the negative electrode and oxidation or an anodic reaction at the positive electrode. But generally, when industry talks about anode and cathode, it's from the primary battery perspective. Quite a range of different chemistries and materials. So this is just a selection of negative and positive active materials for a range of different primary batteries. A few notable points that the negative material, there's quite a lot of lithium, quite a lot of zinc. So when you're building a battery, you want a large potential difference between the two electrodes, and so metals such as lithium and zinc and others allow that good cell voltage and potential difference between the positive and negative material. For secondary batteries, it's a bit of a subset because you need to ensure that the processes are reversible, so both the positive and negative active materials can be converted back to a charged state. And again, plenty of lithium, a bit of zinc, lead. So we'll mainly talk about lithium and lead for secondary batteries. They're the largest two chemistries currently on the market. Nickel metal hydride and nickel cadmium also fairly prevalent, but I think for fever, it's more likely to be lithium and lead that are going to be used in terms of secondary batteries. Just looking at some of the nomenclature as well. Looking at the equilibrium potential, standard potential. So the equilibrium potential, when there's no current flowing, what's the cell voltage? Standard potential is under standard conditions, so unit molarity, standard temperature and pressure. A few constants: gas constant, Faraday's constant, and the number of electrons involved. So whether you're talking about lithium as a single valent ion or lead, say, as a 2-valent 2+ ion, and the chemical activity of the species is important in how the active species react at the electrodes. What have we missed out? So yep, temperature and overpotential, and we'll come on to overpotential a little bit more later on. But that enables you to link the Gibbs free energy to the electrode potential through the number of moles of electrons and Faraday's constant, and a fairly obvious but fundamental one: the cell voltage is always the potential of the positive electrode minus the potential of the negative electrode, so that you always have a positive overall cell potential. Just looking at some generic reactions, if you have a material A, the positive electrode, being converted to C with the addition of electrons, and conversely at the negative electrode, active material B going to D and releasing electrons, you've got an overall reaction of A plus B goes to C plus D. And you can start to use those generic or specific chemistries to work out how the cell potential may change. One of the fundamental equations is the Nernst equation. This is only applicable for zero current, so open circuit potentials only, but it relates the standard potential to the potential you're actually seeing via the constants of the Faraday's constant, the gas equation, gas R, and temperature, along with the activities of the reduced and oxidized species. And often that's instead of the activities, the concentration is used as an analog for that. But effectively, what you're sort of seeing is that the potential will change as a function of temperature and the activities or concentrations, availabilities, and activities of the species involved. And you can work through that to add the two together. So the overall cell potential is the individual positive potential minus that of the negative, and you can get the Nernst equation for whichever battery chemistry that you want to look at. As I said, the Nernst equation only holds true under open circuit conditions, so when there isn't any current flowing. When there is current flowing, there are additional losses within the system, and they are associated with the ohmic losses through the components of the electrodes of the battery, along with overpotentials for the positive and negative electrode reactions, and they can be activation penalties or mass transport penalties. But effectively, when you're charging, the voltage is more positive, and when you're discharging, you're losing those overpotentials and ohmic losses, and the voltage is lower. So what does that sort of look like schematically? Effectively, if you've got the two potentials for the electrodes that you're operating with, under discharge you've got a lower voltage, but on charge you've got a higher voltage. We take a quick look at a couple of those batteries that I mentioned, the lead acid and the lithium. We'll start with lead. There's a range of different architectures that you can get lead acid batteries in, and they range from SLI, so starting lighting ignition batteries, where their use requires a high power but relatively low capacity. So you can probably see on the right hand images big, large, chunky lead connectors to allow the current to flow with low impedance. Towards the left, the Enesis and the Sonnenscheiner battery are storage batteries for lower currents but longer duration operation. So they're for storage rather than requiring higher power. And again, you can sort of tell that from the fairly small electrical connectors and tabs that are there. They're made for long duration, low current and capacity, rather than a big wallop of power to turn over an internal combustion engine. But effectively, they all work on a similar principle. So at the negative electrode in the charge state, you've got lead and lead dioxide. Perhaps it's worth putting a pointer on. Let's see if we can do that. Can you see the pointer? There we go. So in the charge state, at the negative electrode, you've got metallic lead and solid lead dioxide, and the electrolyte is an aqueous solution of sulfuric acid. During the discharge process, there's an ionization or chemical step where the lead is converted to lead ions and then combines with dissociated sulfate from the electrolyte to form lead sulfate. At the positive electrode, that lead dioxide again there's an ionization stage and there's a conversion from lead dioxide to lead 4 plus and hydroxide OH minus, and then conversion through an electrochemical route with lead 2 plus minus 2 electrons going to the lead sulfate. So effectively you're going from lead and lead dioxide to lead sulfate at both of the electrodes, and you're losing some of the free acid and generating water in the electrolyte. So there's a change in the composition of the electrolyte and the active species, and that gives you a corresponding voltage change for the system. Looking at lithium chemistries now, there's a range of different lithium-based batteries identified either by their positive electrode material or the negative electrode material. So NMC, NCA, LMO, LFP, LCO are common shorthand versions for the active materials and identify the slightly different chemistries within the system. Effectively, they all operate on the same principle, however, with two electrode materials where you're shuttling lithium ions from one electrode to the other. So you've got intercalation and deintercalation at the two electrodes during the charge and discharge process. So the charge carrying species is the lithium ion for these batteries. And just as an example of one of the chemistries, so you've got a lithium and metal oxide intercalating more lithium at the positive electrode during discharge rather, and at the negative electrode the lithium from a lithium graphite intercalation complex is releasing lithium to then go across to the positive electrode. So the overall reaction is you're shuttling the lithium from the graphite to the metal oxide. We sort of mentioned the voltage losses and how the voltage profiles are built up for batteries. This is just an example of a charge and discharge profile for a lithium ion cell, an 18650 cylindrical cell, and effectively what you've got is the black line is showing the cell voltage during charging till it hits the voltage limit of just over 3.5 volts for the cell, and then it's discharging, and there's a gradual decline in the voltage until it drops off rapidly. So it drops fairly rapidly to start with due to activation losses, and then the rapid drop off at the end of the discharge is due to the full shuttling of lithium. So there's no more lithium ions to shuttle from between the electrodes. They're fully intercalated into the discharged state, so the voltage is not then sustained. The red line is just the cathode voltage or the positive electrode voltage, and the blue line is the negative electrode voltage, and obviously the sum of the two gives the black line. The other type of battery that may be of interest to Fever is flow batteries, and they work slightly differently to lead acid and lithium in terms of their construction. So both lithium and lead acid, the active materials are fully encased and enclosed within the unit cell, whereas with flow batteries, the active materials are solvated into reservoirs of electrolyte, which are held outside of the stack. So in this schematic, you've got a tank holding an electrolyte and a set of cells that the electrolyte is then pumped through during operation. Some systems have a single electrolyte where there's separation of the charge state by phase change, or others where there's the active material stays solvated throughout all states of charge and discharge. You can have 2 electrolyte tanks to pump between. Another variation may have 4 tanks, so it's a single pass system where you're pumping from a charged tank to a discharged tank for each of the 2 electrolytes. But the main principle is that you've got the active materials being pumped through a cell rather than the cell containing all of the active materials. And there's some advantages to that in terms of the reduction in non-active material usage. So there's some efficiencies and lower casing and other materials being used. Typically, again, for flow batteries and also fuel cells as well, they're arranged in a bipolar stack where you have a single negative end plate, a single positive end plate where electrical connection is made, and then the cells are separated by electrodes, where on one side they act as the positive electrode, and on their other side they act as the negative electrode. So they're electrically conductive but ionically non-conductive. So you're able to separate the cells and have a flow of current through the stack of cells, and the electrolyte is pumped through each side of the cell with a membrane, ion exchange membrane, separating the 2 half cells. And so where the species are solvated at all states of charge and discharge, that 2 electrolyte system and separation is required to stop chemical discharge occurring. So if the electrolytes mixed, there'd be a chemical discharge rather than being available for electrically discharging. As with conventional batteries, there's a number of different flavours and varieties of flow battery and a number of common redox couples. Again, the idea being trying to pick couples that have a reasonable voltage potential to have a good voltage per cell. We've sort of mentioned some of the different types. There tends to be four different varieties, shall we say. So one example is the all vanadium, and as I said, the active species stays solvated at all states of charge and discharge, and you're shuttling between V3 and V4 on one side, and V2 and V3 on the other. V4 and V5 and V2 and V3. Sorry, I've just got a message. I was just checking it wasn't a message from the chat. So you're shuttling between the oxidation species, oxidation states of vanadium. Membrane is needed to stop the V2 and the V5 self-discharging if they mixed. Another type is half redox flow battery, half metal flow battery, and so you've got a phase change. An example is the zinc cerium system. So in the zinc cerium system, you have a phase change at the negative electrode, and you're electroplating zinc during the charging reaction and dissolving it again during the discharging reaction. So there's a phase change there. The cerium is shuttling between cerium 3 plus, cerium 4 plus, but stays solvated in the electrolyte. The third type is a metal oxide. So the example would be the soluble lead. There you've got a phase change at both electrodes. So at the negative electrode, you're going from solvated lead ions to metallic lead during charging, and the positive electrode, you're going from solvated lead 2 ions to solid lead dioxide at the positive electrode. So a phase change at both, and that means that the charge state physically separates the lead dioxide and the lead. So you only need a single reservoir because there's no chemical contact between the two charged species. So there's no chemical self-discharge. The last type is a half unitized fuel cell. So looking at sort of a metal air system, for example, where half of the cell, the positive electrode, is similar to a fuel cell. So you've got a bifunctional air electrode. So you're using that for the positive electrode, and at the other electrode, in the zinc air example, you've got the same reaction as the zinc cerium system, where you've got zinc 2 plus ions in solution being converted to metallic zinc during the charge, and then reversed during discharge. That brings us on to fuel cells. Again, similarities with flow batteries and other conventional batteries in terms of electrochemical conversion of chemical energy to electrical, but they require a supply of fuel. Generally, fuel cells operate with a higher efficiency than burning combustion. But that only takes account of the processes acting inside the fuel cell and is not looking at fuel storage or conversion. Generally, there's a number of common types of fuel cell. The most obvious is PEM, the polymer electrolyte fuel cell. There's also the phosphoric acid fuel cell, where you're using hydrogen as the fuel and air as the oxidant, so oxygen from the air. There's direct methanol fuel cell. Again, you're using oxygen from the air as the oxidant and methanol as the fuel. The alkaline fuel cell, again, using with these two, you've got a proton exchange membrane, so you're shuttling protons from one electrode to the other to maintain charge balance within the system. With the alkaline fuel cell, it's similar to the PEM, so you've got oxygen and hydrogen, but here you've got an alkaline environment, so the charge balance within the cell is made using hydroxide ions. Then there's molten carbonate fuel cell, where you're combining air and carbon dioxide and hydrocarbons as a high temperature system, so thermal control is needed. And then also solid oxide fuel cells, where you're using air and hydrocarbons, again high temperature systems. Within fever, it's more likely to be the PEM or DMFC that are going to be applicable. So if we look at the proton exchange membrane in a little bit more detail, effectively you've got two flow fields to allow the supply of hydrogen and oxygen into the system, and they're usually graphite or similarly conductive but chemically inert materials, so that you can then stack up cells in series in a bipolar configuration. Within the cell, you've then got a gas diffusion layer, which allows the flow of either the hydrogen or the oxygen, but doesn't allow the flow of any other species. And you've got a catalyst layer on the top of those gas diffusion layers, either platinum or other catalysts for the two reactions, separated by a membrane that then allows proton transport and water transport as the byproduct. And overall, you've got hydrogen coming in, dissociating to or ionizing to protons. The protons are going through that membrane to the cathode, where they're reacting with electrons and oxygen to generate water, and power is generated on the external circuit. In terms of operation, similarly to batteries, the ideal or the open circuit voltage is always lower than the ideal, and then as you start to operate the system and draw current, you get a polarization curve that is made up of a number of losses. There's ohmic losses, activation losses to do with the kinetics of the reaction processes, and then concentration losses. So at very high currents, you are starving the reaction sites of hydrogen and oxygen, and so you have mass transport limitations. So you've got effectively three regions where in the first one the activation losses associated with the electrochemical reactions dominate, and then a steady ohmic loss before you get into a mass transport controlled region where you are limited by the supply of hydrogen and oxygen to the catalyst centers. What that means in terms of power output is a peak power generated through from the cell voltage. So if you plot the cell voltage against the current or the current density per unit area, you have the polarization curve that we saw previously. But then when you multiply up the voltage by the current to get the power, you get a peak power region for the fuel cell, and particularly the fuel cells you want to be operating at the most efficient point. Hence where you can bring in some hybridization, so you're always running the fuel cell at a optimum efficiency or power output, and either supplying a load or charging a storage battery with excess power. That's pretty much a whistle-stop tour of batteries and fuel cells for today. The main sort of point really in terms of the electrochemical systems is that the voltage and power output depends on the chemistry, depends on ohmic losses, the flux of materials, so mass transport, temperature, the state of charge for batteries at least, and the load that you're trying to draw. So rather than just a black box that provides a set voltage or a set current or power output, the characteristics of the electrochemical devices vary depending on the usage profile, but also external factors such as the temperature or internal factors like their state of charge. So that's where we'll stop. And if there are any questions, I'm happy to answer. If I can try and stop sharing. There we go. Okay. Any questions or discussion points? I know I sort of rattled through pretty quickly, really, but it was really just to give a bit of an overview, an introduction, and hopefully identify some of the factors, particularly for the modelling, in terms of the voltage and current profiles that we might get out of different systems.
Thanks, Richard. It's really interesting. Well, for me, it's quite not being a chemist. Yeah, I think I'm not sure you talked pretty much about the but maybe I misunderstood. It's a steady state performance. So characteristics of the batteries. I think would be what I don't, as you know, when you charge and discharge, you get this dynamic, and from my electrical point of view, it's like an RC circuit. But I don't know whether you could sort of give an insight into what these things mean.
Yeah, absolutely. So in terms of the modelling side for the electrical circuit, you can put together an RC model that mimics the voltage profiles for different current draws or power delivery. I guess in terms of those models, they tend to look at from a set point, and they don't take account the state of charge. So as you get towards the end of or low states of charge, the voltage drops off further than it would under normal operation. So that they'll do for a general model, but then you need to look at the capacity of the system to then input some additional terms into that RC circuit to take into account the additional voltage losses as you discharge the batteries. I'm not sure if that answered.
Over potentials. I mean, just when you look at slow discharge or in your chemical expressions, you talk about overpotentials and so on.
Okay, sorry. Yes.
Then you model that as an RC circuit, and in real time, if you have a step, for example, increase in current, or if you stop discharging, it takes time for the voltage to rise to the.
Yes. So that's to do with the activation losses and the mass transport effect. So if you have a voltage level for the open circuit state of the battery, if you try and discharge, there'll be a concentration profile from the electrode surface through into the electrolyte, so that there's some losses associated with that, or rather some delay. So in terms of that delay that you're talking about, in terms you're hammering the battery, then you turn it to open circuit, and there's a delay in the equalization of the voltage to that open circuit. So some of that's it's effectively the polarization side of it, and often that's to do with the activity of the species and the flux of the species. So you get a different concentration at the surface of the electrode compared to within the electrolyte, and you get it takes a time to equilibrate, and that's where you're getting the voltage tail, as it were. Not sure I explained that very well.
It makes sense. It makes sense.
So effectively, you've got losses associated with ohmic losses. So it's just like a resistor. So that's a typically linear ohmic relationship. then there's flux of material and activity of the material. So you've got to get the active species from if it's lithium from one electrode to the other through the separator, and there's you have a concentration profile, and obviously as you go to higher and higher currents, you're using the utilizing the active material at the surface sort of quicker and quicker, so that concentration profile expands, so then it takes a longer time to equilibrate when you go to open circuit.
Yeah, are those times shorter in a CF low cell because you get more steering or something, or?
That's a really good question. I think it depends a little bit on the system. So within the within the flow cell, you as well as the sort of normal convection and migration and diffusion, you've got forced convection. So you can suppress that concentration profile by increasing the pumping rate. But depending on the system, there are still there is going to still be a little effect from that. But yes, you can actually see that if you say with a flow battery, if you operate it in a static non-flowing route at a particular current density and then ramp up the flow rate, you can see that that's a suppression and quicker relaxation to the open circuit potential as you increase the flow rate. And again, you can't do that with normal batteries, but an equivalent would be heating it up. So the hotter it is, the more mobile the species are in the system. But obviously, you don't really want to be doing that with, say, lithium, or beyond a certain point, anyway. But as I think the main thing for fever is just the appreciation of the different voltage curves that we get with different electrochemical systems, and particularly if we're combining multiple battery chemistries or fuel cells or others, that they have a different voltage profile during charge and discharge. Again, actually, you know this, Solomon, from the work you've done with lead acid and lithium, that you've got to try and not just match a number of 3.5 volt lithium cells to 2 volt lead acid cells in a 2 to 3 ratio, but you've got to look at the whole voltage window of sort of 4 and a bit volts all the way down to sort of 2 and a bit for lithium, and the sort of 2.2 down to 1.2 volts for the lead acid. So I think that's really where sort of the main point for fever comes in, that it's looking at the batteries as a dynamic and fuel cells as well as a dynamic system that has a different voltage and current profile and power profile, not just as you're pulling higher currents, but also at different states of charge for batteries, different temperatures, and temperature affects different chemistries slightly differently.
That's a very good point, actually. Those RC capacitors as well, the transient has a significant effect. It's not like power link to DC power supplies, where they share with accordance with the resistance. It's a bit more complicated. So the dynamics comes into it.